All right, so this video is going to be a solution for this potential energy homework set that I have. So the first question here was to consider a mass connected to a spring. And so this says that you have a mass of m connected to a horizontal spring with a spring constant of k. The mass rests on a frictionless table with the spring connected to the wall as shown. So here is the picture here for our mass on a spring. Okay. Now, this is going to be the equilibrium position, right? And then we're going to drop back to some distance of a. So here's some distance of a, and then we can say that we drew the spring back by an amount like this. So this is going to be the distance of a. Okay. And so the first thing that we'd like to do is we'd like to determine what the potential energy function is going to be. Okay. So in order to determine the potential energy function, we're going to recall, this is 1a, that the potential energy as a function of, in general, as a function of r, is going to be equal to the integral of F for whatever conservative force that we have here, dot dr with a negative sign on the outside. Okay. Now here, when we're talking about this spring, we're going to say this is the plus x direction. And so that says that dr vector is going to be x hat dx. Okay. And so the force of interest here is going to be the force of a spring. So this is going to be u sub s and f sub s. And so here, this says this is going to be the integral of the spring force, which is going to be minus kx x hat dot x hat dx. This is dot product between x hat and x hat is 1. And so this is going to have a negative sign on the outside. So this is going to be the integral kx dx, which is going to be equal to k integral x dx, which is going to be equal to 1/2 kx squared. In general, this is going to be plus constant integration, but we're choosing our coordinate system in such a way that that is going to be 0. So the potential energy function, u as a function of x for our spring, is going to be given by this function that I have here. Okay. So that's the first part. The next part that we're looking at here says that the spring is drawn back by a distance of a and then it's released from rest. Determine the velocity of the mass when the spring returns to its equilibrium position, i.e. when x is equal to 0. And that's actually what we have in this situation here, right? So we have, this is our state 1, this is our state 2. And one way that we found that was really useful to think about these situations is to draw some energy bar charts. So if I was going to draw some energy bar charts here, to say that here is my state 1, and here's my state 2, here is my kinetic energy, K1, and then U1, and we have our kinetic energy, K2, and U2 here. Now we see in the state 1, we actually, this is actually after it's been released, so let me, we'll just leave it like this. But in state 1, it's moving, right? And it's also at its equilibrium position. Looking at our function for the spring potential energy, if x is 0, potential energy is 0. And so that says that all of our energy is going to be in the form of kinetic energy. Okay? So we have all kinetic energy. In the state that I have labeled 2, this is when it's drawn back and we're releasing it from rest. So it's not moving. Kinetic energy is going to be 1/2 mv squared, and so the kinetic energy is going to be 0. And so we have all potential energy. Okay? So then what we can do is we can say that really K1 plus U1 is going to be equal to E1, and K2 plus U2 is going to be equal to E2. And the statement of conservation of energy is that E1 is equal to E2. And we can see that by these bar charts because they're the same height. Okay? So then what we can do is we can say that K1 plus U1 is equal to K2 plus U2. But based on our bar charts, we see that K1 is going to be non-zero, U1 is 0, so that's 0. And then in state 2, K2 is going to be 0. So this ultimately says K1 is going to be equal to U2. And so ultimately what we're going to have is 1/2 mv1 squared is going to be equal to, excuse me, this is going to be equal to 1/2 kx2 squared, okay? Where v1 is the velocity we're trying to solve for, x2 is going to be equal to a. And so we just do a little bit of algebra here, and we end up seeing that v1 is going to be equal to the square root of K1 over M times A. Okay, so that's our question 1B. Okay, so let's grab all this stuff and then move it down here so that we're in the same spot. And then we'll move on to our next portion, which is going to be considering what happens when we're on the other side. And now what we're going to have is we're looking at the spring has gone past this this equilibrium point. So you can imagine the motion here. We drop back. It's going to be pulled towards the center, but it's not going to stop at the center. It's going to go past it, right? So here, now what we're going to do is we want to find the maximum distance the spring is compressed after it moves past its equilibrium position. And so we can call that some different distance. We'll call it some distance d. And so here, let's redraw our situation for exactly what we're doing here. So this is going to be 1c, I believe. Yep. So this is going to be 1c. And so the situation that we're going to have is here's our state 1, right? So now this is x is equal to 0. And it's moving with this velocity that we found, v1. Okay. Then it's going to compress the spring a certain amount. We don't know what that amount is yet, but we can say that this is some distance of d. Okay. We want to find what this distance d is. Again, what we can do is we can go to our energy bar charts, and so we can say that here we're going to have, let's call this state 2. Actually, that's what I called state 1 before, but let's keep it with a 1, 2 notation. So this is going to be state 1, this is state 2, and so we have 1 and 2. This is K1, U1, K2, U2. So in this case, we have all of this is going to be in kinetic energy initially, right? So we have all kinetic energy. And then we have, in the state 2, all potential energy, okay? So again, we can say this is really kind of feeding into our conservation of energy because K1 plus U1 is equal to K2 plus U2. And then here, this U2, or sorry, U1 is 0, K2 is 0, so 1/2 mv1 squared is going to be equal to 1/2 k. We can say that this is going to be some x2, or what I have here is this. We'll leave it like that for now, but this is really this unknown distance I'm calling d that we're trying to solve for. Okay, so do a little bit of algebra, and we can cancel this and this. And what we end up seeing is that x2, which is what I'm calling d, so d is going to be equal to the square root of m over k times v1. Okay, but we know what v1 is, so we can take that and we can plug that in here, and we're going to see something rather interesting. So when we plug that in here, we say this is going to be root m over k times root m over k. Oh, those are going to cancel. Times a. So those go away. And so what this says is that the distance t is going to be equal to a. So this is symmetric. It's going to go the same displacement here. This d is really the distance a. And we've proven that by kind of connecting our steps through our conservation of energy. Okay. The next part. So this is going to be 1d. So 1d says find the maximum speed of the mass when the spring is, or find the speed of the mass when the spring is half its distance to its maximum displacement from the equilibrium position. So now what we're going to do is we're going to say that here, let's draw this again. So we have, so we'll draw this again, and we have, here's our mass on the spring. Here is our equilibrium position. And what I'm actually going to do here, because it's a little bit easier to do it like this, because that way it saves me a step, and you'll see why I'm doing it like this. I'm going to draw 3 situations here. Okay. Now, this isn't drawn to the same scale that I had before, and you're going to have to use your imagination, because even this isn't the same scale that I want. But this is going to be x is equal to 0. This is some distance a divided by 2, and this is some distance of a. Okay. So really, I have 1, 2, 3. And we can, again, draw our energy bar charts here. So we have some really big, long bar chart here. So this is going to look like this. here is 1, here is 2, here is 3, and then we have our K1, U1, K2, U2, K3, U3. Okay, and so we know what's going on in states 1 and 3, right? Because here we're going to have all kinetic energy, and then over here we're going to have all potential energy, and those two bars are the same height because energy is conserved. But then somewhere in the middle, we're going to have a little bit of combination of both, and they're not going to be exactly the same height. For the sake of right now, what I'm going to do is I'm going to make them the same height. And then when you look at these two bars here, when you add them together, you get the other two bars. So really, what we have here is K1 plus U1 is equal to K2 plus U2, which is going to be equal to K3 plus U3, or E1 is equal to E2 is equal to E3. So this is really what we're saying with conservation of energy. It's not just a point and a point. It's the whole thing that the energy is going to be constant. And so now what I can do, if I want to find what this velocity is for this one, right? So let's say that this was moving like this, and call it some V1, call it some V2, and then it stops over here at A. A is the thing we know already, so it algebraically is a little bit easier to solve for that instead. So I'm going to use E2 and E3 here. And so when I do that, what I end up seeing is that what I end up seeing here is that 1/2 mv2 squared plus 1/2 kx2 squared is going to be equal to 1/2 kx3 squared, 3 squared. Right? Okay. But here we know what x2 and x3 are, right? This is x2. This is x3. Okay. So take this and then evaluate for that. So this is going to be 1/2. Let's, even in this step right here, let's get rid of our 1/2s, because every term here has a 1/2. So get rid of that, get rid of that, get rid of that. And then evaluate this. So this is going to be mv2 squared plus k, this is going to be a divided by 2 squared, is going to be equal to k a squared. Move this around and solve for v2. v2 is going to be equal to the square root of k over m. And then when I move this over to the other side, when I square this is a quarter, 1 minus a quarter is a third. So this is going to be root 3k over 4, which gives you a 2. So this is going to be a divided by 2. Okay, and that's our velocity. Okay, so we go with that one. Now, the next question asks us to plot this. So we got speed when it's half the distance. Now we just want to do a plot. And so the easiest thing to plot really is the potential energy, right? Because that we have some function for, right? We're told, or we found that this was going to be 1/2 kx squared. So we know what plots of x squared look like. This is going to be like this. So here's, actually I want to plot this symmetric for negative x and positive x. So this is going to be the positive x, this is plus x, this is going to be minus x, and this is going to be units of energy as a function of x. And so U, our potential energy, is going to just be this parabola, like this, right? So there's U. We know that the energy is going to be constant. So the energy is the same this entire time. So if the energy is the same, then it's just going to be some horizontal line, okay? So call this right here, call this one E as a function of x, which is really just going to be a constant. Call this one U as a function of x. But if we write that E is going to be equal to U as a function of x plus k as a function of x, we can rearrange this to find what k as a function of x is explicitly. So we have E minus 1/2 k x squared is going to be equal to k as a function of x. And so this is also a parabola where this is just going to be inverted. And so this is going to look like this now. So we have something that looks like that, okay? And that's really meant to touch this line here. I just didn't draw it quite to scale. So it's coming up like that. Okay. So now let's look at this and think about what we have in terms of what we found here. So this is our k as a function of x, and this right here, this is the distance minus a. Or it is a distance of a, but it's along the minus x direction, so this is a. And then drawn this to scale, this would have come over a little bit over here, but this would also be this distance of a. Okay, so that's what our plot looks like. Good. So now let's move on to the next question. And so the next question said we had some kind of roller coaster like this, right? So we're going around some loop. There's a circular loop with some radius of r. This is going to be some height of h. And there's a mass of m right here. And the first thing that we want to do is we want to find what the velocity is at this point 1. And actually, in retrospect, I wish I had drawn this, or I wish I had described this a little bit different. Call this the point 1, call this the point 2, and call this the point 3. Okay. So now, this is going to be 2a. We want to find the velocity at 2. Okay. Now we could write our energy bar charts, but we end up, once we're going through this process, we realize that the tool is really leading us by the nose to the equations anyway. And so what we can do is we can say, okay, let me think about what's happening at the point 1. Well, what's happening at the point 1, it's not moving, so there's no kinetic energy. It is some height above the ground, so there's gravitational potential energy. And so then what I can do is I can say that, write an extra step here, like this. E1 is equal to E2, right? So then the question is, what is E1? E1 is all gravitational potential energy. This is going to be mg times capital H. What is the energy at 2? Well, I'm defining my ground to be right here. And 2 is essentially, it's like at ground level. You can see in the picture it's not exactly, but we're going to say that it is. And so that means that it's going to be all kinetic energy. So this is going to be equal to 1/2 mv squared, or v2 squared. Okay. So we want to find v2, do a little bit of algebra, cancel our m's. We see that v2 is going to be equal to 2gh square root. Okay. Next part, 2b. We want to find what the energy is going to be, or sorry, what the velocity is at point 3. So in order to find the velocity at point 3, same idea. We say that the energy E1 is going to be at the energy at E3. And so this is going to be mgh. It's going to be equal to 1/2 mv3 squared, right? Because we know that it's going to be moving here, right? But it also now is some height above the ground, right? So this is some height above the ground here, where this is going to be 2 times the radius, right? Because radius goes like that and that. So that's r and that's r. So we'd have double the radius here, right? So then what we can say is this is going to be plus mg times this height that we have, which is going to be 2 times r. Solve for v3. So we move this to the other side. We can cancel our m's. Not our g, or m. We can cancel our m's. And then we have g times h minus 2r is going to be equal to 1/2 v3 squared. And so v3 is going to be equal to 2g h minus 2r times, or with a square root over it. Okay, so that's, here's our 2a, here is our 2b. The last part that we want to take care of here is we want to find the condition for what is the relationship between h and r if this mass just barely gets around, okay? So in order to answer that question, this is actually kind of coming back to circular motion. So let's draw a free body diagram here. So when this is in contact with the track at the top, when we're looking at the forces on it, there's some normal force N. There is some gravitational force mg. So if I was to sum my forces in the radial direction, calling outwards, out of the circle, the radial direction, right? Because radial means away from the center. This says that the sum of the forces in the radial direction is going to be equal to minus n minus mg, right? Because it's going to be in the negative direction. And this is going to be equal to this is going to be equal to m times acceleration in the radial direction, okay? But we want to parameterize this in terms of velocity, and we remember from our analysis previously when we did circular motion that the acceleration in the radial direction can be written as, this is going to be minus v squared divided by r, okay? And if this is going to be constant circular motion, which it's actually not, then this is true for the whole circle, right? But this is also, if you're considering this velocity to be a function of time, then this actually is true in general. You just, you have to be careful in thinking about this. What we also saw is that this is only true for circular motion. If we're talking about elliptical motion, of course, it's going to be a little bit different. Okay, so plugging that in here, what we end up seeing is that n plus mg is going to be equal to v squared over r. Okay. Now the condition that it loses contact with the track is when the normal force goes to 0. Right. So we lost a mass here. So the normal force is going to go to 0. And so what this says, we can cancel our m's. We can cancel our m's. And so the condition that we have here is that v squared is going to be equal to g times r. Right? I'm going to make it a capital R because that's the actual radius that I've given you in the problem. Okay. So now, this is v3, right? So v3 squared is going to be gr, or the square root of v3 is going to be gr. The square root of, v3 is going to be equal to the square root of gr. And so we can use that in conjunction with this up here to form our condition for when this just barely makes it around the track. And so what that says then is that gr is going to be equal to 2gh minus 2r. We can expand this and move some things around. So we end up seeing that, excuse me, we end up seeing that gr is going to be equal to 2gh minus 4gr. We can cancel all of our g's. Let's cancel our g's. Move our r to the other side, so we're going to have 5r is going to be equal to 2h, or h is going to be equal to 5 halves r. Okay. And so this seems to make sense in some regard, because if we found something like h is going to be equal to half r, that doesn't make any sense, right? Because r, it has to be larger than r. It also has to be larger than 2r, right? Because if h is less than 2r, then that's not even as high as the loop is going to be. So it needs to be larger than 2r, and it turns out that that larger than 2r is going to be 5 halves r, or it's 2.5 r. Okay, so that's going to be it for this video. I hope you guys enjoy, and good luck studying.